Thanks very much, and thanks for inviting me to come up and talk tonight. That was a pretty impressive introduction. Thanks very much. I've got a lot to live up to tonight. Anyway, so really what I want to focus on now is a couple of issues. You've heard a lot of people talk about the fact that we're in a climate emergency now, particularly the students. They've been out on the streets around the world, including in Canberra as well, claiming that we have an emergency. So I'm going to talk a little bit about the science of why the students are probably right. We probably are now just entering an emergency situation. And then I'll talk a little bit about my favorite topic, which is putting climate into a much broader context of planet Earth, how it operates, and where we might be going. So let's see, there we go. Yeah, this is what's on everybody's mind, including around the world. I've had an enormous number of messages from my colleagues saying, are you really on fire? Is Canberra okay? That sort of thing. So I spent a lot of emails saying, no, we're okay. Bit smoky now and again down in Canberra, but okay. So this has really got the minds of people really focused on climate change. This photograph was taken in Tuggeranong, if you know Canberra, southern suburbs. These were some of the ones that were on alert to evacuate. If you know Mount Tennant or the Namadgi National Park, that's what's being burnt in the background. We were very lucky. We got a wind shift, and this did not come down into Canberra as it did in 2003. So that's what it looked like in early January. In fact, some of our good friends, this could have been taken from their balcony. They were getting ready to go. If you sort of put your gaze up a little bit like the satellites do, that's what Eastern Australia looked like in January. There was so much smoke, of course, that went all the way across, obviously, to New Zealand. I was over in New Zealand in January. The Kiwis were complaining, yet again, about what Aussies are sending over there. And some of this smoke got high enough that it got into the stratosphere and circled the planet a couple of times. So these were very, very large events. And that's what it looked like on the ground. That's somewhere west of Sydney in New South Wales. One of the things that really was, I think, amazing about these fires was the size of them, the intensity. Some of the flames were 70, 80 meters high, which is why the fireys simply couldn't keep them under control and had to turn around and go. A friend of mine is Greg Mullins. Some of you may know him. He was the former head of Climate and Emergency Services in New South Wales, and he's had 30, 35 years of this stuff, and said he hasn't seen anything at all like what's happened this year. Living in Canberra, I often go down to Bateman's Bay. This is the first summer I did not go down to Bateman's Bay. The traffic was going the other way. This is evacuating the south coast area around Bateman's Bay, again, right around New Year's time, when the call went out that you had to get out of there because you just couldn't cope with the fires. So that's the traffic jam coming out of Bateman's Bay. And back in Canberra, that's what it looked like on the 5th of January at midday. So that's right in the center of Civic, if you know Canberra. That's the Central Light Rail Station. I don't know how many days my wife and I had to put on the mask to even go outside safely. It was pretty horrible weather. When I was working internationally, I've been to places like New Delhi. I've been to Beijing before they cleaned Beijing up. This is as bad as any of those Asian cities ever got. So it was a really big issue. So when you look at some of the statistics, the estimates of how much was actually burnt up and down the East Coast go as high as about 12 million hectares burnt. And to give you an idea of what that is, the area of the country of England is about 13 million hectares. So this is burning something on the order of the area of England or the area of North Island, New Zealand. That's also about 13 million hectares. So a lot was burnt. Unfortunately, 33 people were killed. I think it's amazing that not more were. I think it's just a testament to how well people got out of the way and how much effort the fireys put into protecting people. About 3,000 dwellings and other structures were destroyed. A few villages, Cobargo is an obvious one. Parts of Mogo down just south of Bateman's Bay were destroyed. Over 1 billion animals, and this is mammals, birds, and reptiles, were burnt to death. About 800,000 of those in New South Wales. And of course, everyone has seen the pictures of the koalas and the kangaroos. I've talked to a couple of the fireys, even though they're veterans. It's really hard for them emotionally and psychologically to handle when they see kangaroos on fire, in flames, hopping out and then dying in front of them. It's really tough stuff that they went through. This statistic that just came out a week ago in a paper by some scientists from the University of Wollongong. So this is published in Nature, which is the big science journal internationally. And they had a special issue that came out on the 24th of February, so it's a little over a week ago now, just focused on the Australian fires. So one of the interesting things is you can go around the world and look at comparable forests. So the scientists call these broad-leafed temperate forests. So they're not tropical, and they're not in the northern Arctic zone, and they have broad leaves like eucalypts. So eucalypts are the classic here. And you can look around the world, every continent has them, and we've been tracking fires for 20 or 30 years systematically in all of those. And the average amount burnt in any one year, it goes up and down, but the average in Australia is a bit under 2%. For most of the continents, it's well under 5%. There are a couple of them, Africa can get up to 8% or so, burnt in any one average year. This is the first time we've ever seen any of these anywhere in the world over 20%. So if anyone says, well, you know, we've always had fires, and we have, and fires are part of the ecosystems, and they are, but nothing like this. This was completely out of the ordinary. Haven't seen anything like this. In fact, if you go back to the 1939 fires, it's harder to estimate the area there, but it was somewhere between 4 and 5 million hectares burnt at that time. And this is certainly much more than the Black Saturday fires, much more than the Ash Wednesday fires, more than the Canberra Alpine fires of 2003. So if you look at a map of New South Wales, that red is obviously the area burnt. So when you look at the entire state, now of course a lot of the state does not have forests. It's got agricultural land, so it's got other ecosystems. The forest is the strip down the east coast. So you can see how much was burnt. It was amazing. And you get some of the statistics. These statistics are for New South Wales alone. So they don't account for what happened in southern Queensland or what happened in Victoria. So you see it's a huge area that was burnt. If we just look at west of Sydney, two big fires west of Sydney, these were the Blue Mountains fires up here. And if you look at that in more detail, that's over here. So the yellow plus the green is the Blue Mountains World Heritage Area. So of that, the yellow burnt. So you can see how much is left of the World Heritage Area. The swath up here and then a couple of pockets. Over 80% of that World Heritage Area burnt. The gray areas also burnt, but they're not within the World Heritage. So you can see how big that fire is. There's another one to the south of Sydney. So the first time ever Sydney was put on a catastrophic fire alert, the city of Sydney, for obvious reasons. So obviously these were huge, unprecedented, and the question is, what's behind all this? So that's where the science comes in. So I'll switch now from some photos and some maps to some of the scientific information. So this is back from 1910. So it's over a decade, over a century rather, worth of measurements. And what it's measuring is the maximum temperature. So every day here in Goulburn you have a maximum and a minimum. So there are hundreds of reporting stations around the country. So we can take the maximum on a given day and average it around Australia. That's what the Bureau of Meteorology does. And then what it does is it averages over a year. So year by year, we can see that it's getting hotter. The maximum temperature is going up. But 2019 was unusual. 2.09 degrees above the 1961-1990 average, which is the baseline the Bureau used. So the issue here is that not only has it been getting hotter, this was an incredibly hot year. It was half a degree hotter than anyone we'd seen before in terms of maximum temperature. So that's telling you that the forests out here for the preceding 6 to 12 months, when the fires really started in August, September, were subjected to incredibly high temperatures. And when you look at that spread out over the continent, the western half of the continent all was the highest maximum on record, but the area that burnt also experienced that as well. So it was subject to incredibly hot, highest on record maximum temperatures. Then when you add into that what's been happening with rainfall, I don't have to tell any of you about this. If any of you are out on the land here around Goulburn, you know what's happened the last couple of years, really starting in 2017, but here's the last 2 years, again from the Bureau, 1 January 2018 to the end of 2019. And again, that's color-coded. So this really dark red is the lowest on record. So records go back to 1900 in terms of rainfall. So even with the Federation drought, the World War II drought, and even the Millennium drought, we haven't seen anything like this. So this is about as bad as it could possibly get. And most of southeastern Australia was very much below average. So here you have forests that have had 2 years of exceptionally low rainfall, and on top of that, the hottest conditions they've ever experienced. So the Bureau puts this together in a thing called the Forest Fire Danger Index, FFDI. They've been calculating that from 1950, so we have 70 years of it. There are 4 parameters that go in. It's actually not one thing they measure, it's a thing they calculate. So it has temperature, it has humidity, it has wind speed, and it has rainfall going back in time. So what it's trying to do is tell you when are fires likely to break out. What's really dangerous weather? Well, that's weather that's very hot on the day, it's low humidity, it's windy, and the months and year or two ahead of time have been dry. That's the conditions when fire is likely to break out. But the interesting thing here is from 1950, this index has been going up. So right around here in southeastern Australia is where we see the highest rate of increase of this index. Now they set this index, because remember they started it in 1950. So what would you do? You'd say, we're going to set this 100, the top of the index, at the worst possible conditions. Well, what were they if you were sitting in 1950? They were the 1939 fires. That was the worst that people thought could possibly happen. So those conditions, and they went back and the Bureau had all the data, they calculated what the FFDI would have been in 1939 when those fires broke out and said that's going to be 100. So where are we today? Many places around Eastern Australia, that index was nearly 200 and actually went over 200 in a couple of places. But it was routinely well over 100 all up and down the East Coast. So that's telling you, if you're judging by what were the standard conditions in Australia in the first half of the 20th century and before, this is entirely unusual. And this isn't a one-off. This index has been going up steadily since the mid-20th century. Well, I don't want to focus only on the fires because 2019 had some other interesting extremes. So if we go back to January 2019, a bit over a year ago, again, we had record-shattering heat in that month. A lot of records were broken there. But interestingly, this is Townsville in North Queensland. They had a phenomenal flood, the worst they've ever seen. And they probably won't fully recover. There was so much damage done to Townsville that bits of it aren't going to come back. And at the same time, fires were around a year ago too. This is actually another World Heritage Area, but this is in Tasmania. So this forest is actually a moist, temperate forest. It's not a eucalypt forest, and it's not fire adapted. So we don't think this is going to come back as it was. It'll probably come back as a eucalypt forest or a scrubland. And so that was basically just burnt to the ground. But the interesting thing is when you look at the meteorological data for those events, here's January, the heat wave in January. Again, you can see this temperature color coding. These browns and deep colors are over 40 degrees. So during this 2-week period, it's hard to see. This is the mid-January, 11th to 26th of January. All those areas in red, that's over 80% of Australia, experienced temperatures over 40 degrees. Nothing even close to that had ever happened before. So that's how hot it was a year or so ago. But to me, an even more remarkable one is actually this one. This is a little bit hard to interpret. This is a rainfall record for Townsville. So what we're doing here is this horizontal axis is a year. It starts in January and ends in the end of December. And so obviously most of the rainfall comes in the wet, so it builds up and then it evens off over the cool months and then starts the next season. The black line is the average of what Townsville gets. So it accumulates up to 800 or 900 into 1,000 mils by the end of the year. This red line here was a 8 or 9 day rain event. It's already doubled in 8 or 9 days what the annual total rainfall was for Townsville. That's why it flooded so badly. Again, we haven't seen anything like this on the records. The worst one before that was this one here, and already that red line has broken out of that. So again, you're seeing record heat, you're seeing record rainfalls around the country. And of course, most people know about this, the decline and death of coral reefs. So at a bit over 1 degree global temperature, we've already seen half of the reef gone. So that's what a healthy reef looks like. And of course, when it bleaches, it spits out the little zooxanthellae, the little microorganisms that inhabit the corals. And then the corals turn white because the color comes from the zooxanthellae, not the corals. If the temperature is reduced, these can recover and the zooxanthellae can go back in. So some parts of the reef do recover, but if the heat is too intense or too prolonged, the coral itself dies. And then it looks like this. It gets covered with algae, this cloudy water, the fish leave. And it's not a very pleasant place to go. Nobody would pay a lot of money to come over from America or Europe to see that. They can see that in the Caribbean if they want to see trashed reefs. So this is what's happening to the reef. It's not an isolated case, unfortunately. So over the entire GBR, about 2,000 kilometers, about 50% of the shallow water corals have been killed. So those are the ones you see when you go snorkeling or diving. Off the trenches, there are some deep corals, and they're usually in cooler water. But the big ticket item are the shallow ones. And there were two consecutive bleaching events, 2016, 2017. And climate change made bleaching of the Great Barrier Reef 175 times more likely. Well, how can we say that, number like that? Well, what you can do is what's called an attribution study. So we measured what the temperature of the water was during those bleaching events. We know it was exceptionally warm, a couple of degrees above normal. And you say, well, all right, that's interesting, but didn't that happen before without climate change? So what you can do is run climate models with and without the additional CO2. So you can run them with 280 parts per million CO2, which is pre-industrial, and you can run them with about 405 or so, which is what it was like in 2016. And you can run them thousands of times on big computers. So what you find is that when you put the extra CO2 in, the bleaching happens 175 times more often. It only happened a couple of times without the CO2. So it would have been an extremely unusual event. But with the extra CO2, it was reasonably common. It would have happened about every 10 years or so. Turned out it happened in 2016, 2017. So this is the sort of basis we can say with a high degree of confidence that bleaching would not have happened without climate change. Certainly not to that level. So these are ways in which climate scientists can now try to link, in a very quantitative way, what we actually observe and what would happen with or without the extra greenhouse gases. So, will it come back? The last I heard from Terry Hughes a few months ago, he came to ANU. He's one of the world's experts on corals. He works up in Townsville. He says the recruitment, in other words, the recovery with new corals, the coral larvae, has declined by nearly 90% in 28, indicating an impaired capacity for recovery. So he's pessimistic about, even if we could keep the temperatures down, whether the reef will recover. And of course, as we speak, aerial surveys are going on because we suspect there's another bleaching event going on. There's a pool of very warm water very close to the reef. So the point I keep telling people is, don't expect this is it. Temperatures keep going up as long as we keep emitting, and it's only going to put even more pressure on the reef. But you can look at other ecosystems. These are 4 of them around Australia. This is probably the closest one to us. That's the Murray-Darling Basin, where trees are suffering, again, from heat or drought. This is a kelp bed, or was a kelp bed off Tasmania. It's been chewed by sea urchins, which have moved south on the East Australian current with the warm water. They normally don't live down in Tasmania. They do now. There's the Great Barrier Reef. This is Macquarie Island, which again has suffered from excess heat, the ecosystem there. And we can see the impacts on animals. My colleague Leslie Hughes at Macquarie's put these slides together. Massive fish kill in the Murray-Darling Basin. That's Murray cod. Part of that was due to we took off too much water for cotton growers and so on. But the water that was left got extremely hot, killed the fish. These are baby spectacled flying foxes from Queensland. They're being chilled now. These are really little ones. Their mothers were killed by excess heat and dropped dead out of the trees. The little babies were hanging on to their mothers, and we were able to save some of the babies, but not the mothers. So again, that's excess heat is causing that. Same here. These are Carnaby's black cockatoo from WA. Again, they fell dead out of the trees from excess heat. So these things these creatures that are affected by excess heat, there is no doubt, because that is the one aspect of climate we are absolutely sure is being driven by climate change. That's not natural variability. These are ringtail possums. What happened to them was, again, excess heat, but they crawled to the nearest water source, which was saline, and they died of saline poisoning. So Leslie's put together a report, Climate Council report, called This is What Climate Change Looks Like. So you don't hear much about this, but all around the country you can see evidence of what a heating planet is doing. And the most iconic one of all, of course, is this one. This is before the fires. This is a heat-stressed koala. He's been put on life support to keep him going. So it isn't a one-off that our animals are suffering. They're suffering everywhere. Okay, what's behind all this? It's pretty obvious to scientists. This is global average surface temperature from 1880 up to the present. So the last year on this particular graph was 2018. We don't have 2019 on that. 2019 is up just here. I think it was number 2 globally. So you can see the shape of that curve from about the mid-20th century. It's sweeping up. It's going up at about 2 degrees a century or 0.2 of a degree a decade, and it's accelerating. So there's no doubt that this is way outside the normal. I'll show you much longer temperature records to show you how unusual this actually is. And we know why it's occurring. If you look at the shape of that curve and then look at the shape of this curve, these are fossil fuel emissions. Again, sweeping up from 1950, temperature goes right along with that. The tan colored here are land use change. So that is mainly occurring in 2 places. That's mainly Amazon deforestation and Southeast Asia deforestation. Most of the temperate world, Australia oscillates a bit up and down in terms of our land use, but most of Europe and North America is actually reforesting a bit. But it's overshadowed by the big tropical biomes which are being deforested. The link between those curves is obvious. The basic physics is known. CO2, as it's poured into the atmosphere, forms a belt in the mid and lower troposphere. That's the bottom part of the atmosphere. And what it does is it absorbs some of the heat coming out from the Earth's surface. The heat balances itself by taking in sunlight, heats up, emits heat, different wavelength. So the CO2 is transparent to the sun coming in, but it's not transparent to the CO2 going out. It absorbs some of it, and it re-emits it in all directions. So some of it comes back down to the Earth, and it heats the Earth. That physics has actually been known for 200 years. The first scientist who did that was who worked that out was Joseph Fourier, who's a French mathematician. But it's interesting, the first laboratory proof that this is actually a real phenomenon was done in 1857 or 58. Now, it's only come to light recently. It was actually done by an American amateur scientist, and she happened to be a woman, so she got no credit. Back then, women didn't do science. So everyone thinks it was John Tyndall, who was a physicist from the UK. But in fact, it was a woman named Eunice Foote from the US who did this first. She beat John Tyndall. And it's only recently that people have been able to dig this out of the archives and give her posthumously the credit that she really should have. So this has been known for a long, long time.
Just ask a question.
Yeah.
Explain the difference between the greenhouse effect and the enhanced greenhouse effect.
Yeah, the greenhouse effect is there anyway because we have naturally CO2 at about 180 parts per million, and we have other gases up there. In other words, if we didn't have those gases, the Earth would be 33 degrees Celsius colder, and it would be frozen everywhere. So there are greenhouse gases naturally in the atmosphere, and that's actually good because we mammals couldn't exist without it. So the enhanced means we're putting extra greenhouse gases. That's really what it means. So that's a bit of scientific jargon. We should just say this is the thickening caused by our extra greenhouse gases. So the second part of my talk is really what I work a lot on, which is Earth system science, and that's to really try to study the planet in a much longer time frame and bring in some other processes in addition to the basic physics of the greenhouse effect. So you may have heard some people who don't believe in climate change or think it's all a hoax or something say, well, the climate has always changed, temperature's always gone up and down. Well, it's true, but you actually have to put in perspective what's happening now and why compared to the natural variability. So I'm going to do that here. These are some ice core data I've got here. These are ice cores from East Antarctica. They're in fact from the Australian Antarctic territory, which is where most of the ice coring goes on that goes way back in time. Whether it's the Europeans or the Russians or us, it's all on our territory. So we drill these put these massive tubes down several kilometers into these huge ice domes. and pull out the ice, extrude it out, and then you can analyze it layer by layer, because what that is compressed snow that's gone down season by season by season. The further you go down, the more it gets smashed and you can't resolve it as well as you can the more recent stuff, which you can actually get down to a year or two on the top. Anyway, we can go back 400,000 years, which is what we're doing now. It's not 400, it's 400,000. And this is a Vostok ice core. The red jagged line is a proxy for temperature. So they can look at isotopes of hydrogen and oxygen and work out what the temperature of the Earth was. And here's the scale. It goes from around 0 to -8. Now, when you take into account, there's a polar amplification of a factor of 2. So for a global average temperature, the poles are twice that. So it's exaggerated, either heating or cooling at the pole. What this is showing us is 4 cycles of ice ages and warm periods. So you've all heard of ice ages. This is what they look like in an ice core. It takes a long time for the big polar ice to form. That's why it takes why it's a long time to form a full glaciated state. And it's a pretty rocky ride, too, as you can see. So the last glacial maximum was about 20,000 years ago. But interestingly, we humans can be mapped entirely on this graph. So we evolved about 200 to 250,000 years ago in Africa and started moving around the planet about a little after 100,000 years ago is our best estimate. So the first wave of humans out ended up in New Guinea and here with indigenous Australians about 65,000 years ago, but they left Africa 20 to 25,000 years before that, and they slowly made their way around. But all through this time, we were hunter-gatherers everywhere, no matter what continent and who we were, what culture. It's only in this last 11,700 years that we have been able to develop agriculture. So if I take the last 100,000 years and just blow it up a little bit, you can see a little bit more detail on this ice core. Again, you see the Earth going into an ice age. This is as cold as it got. And then we have this fairly sharp rise. That's triggered by changes in the Earth orbit. And so what it does is it changes the distribution of sunlight, puts a bit more on the northern hemisphere continental ice, the big sheets over Europe and North America. They start to melt, and when they start to melt, they retreat. And what happens when they retreat? They uncover darker land. That absorbs more sunlight, and it accelerates the warming. And what happens when the oceans warm? CO2 is less soluble in warm water than cold. It starts bubbling out CO2. But what you find is very soon after that happens, CO2 jumps into the driver's seat, and when we look at fine scale ice core data, CO2 leads the temperature rise from about here on up. So it's a combination of absorbing more sunlight and pumping CO2 into the atmosphere that warms the planet. So CO2 goes from about 180 parts per million to 280. But the thing I want to point out now is what we're doing to the climate, what that looks like compared to the ice cores. So there's the graph I showed you. That's about 140 years or so. But what I want to do is take the last bit of this warm period we're in, the last 2,000 years. We got very good temperature data for that. That's the Roman Empire, okay? So Europeans came to Australia somewhere around in here. So this encompasses a lot. The Mayan civilizations in Mexico were here and so on. And yes, temperature goes up and down. That's global average temperature. Got pretty good records there. But you see these blue lines, say there are limits within which it sits, and those limits are about 1/10 of 1 degree either side. You wouldn't feel the difference if you were on the planet. 1/10 of 1 degree. And there's been an exceptionally slow cooling event, a cooling trend. That's because of the Earth's orbit. If you look at the Earth's orbit, this was predicted to stabilize out in the next few centuries and then sit flat for about 1,000 years and then perhaps start going into an ice age. So we can predict all that from our models. But this is the human influence. So that's the 1880 to 2020 temperature record. And here you see the mid-20th century. Here's where it's starting up and going there. But on that same scale, you can see how dramatic that increase is and how fast. This is why ecosystems are falling over. Ecosystems, animals, are adapted to that, wherever they sit on the planet. They are not adapted to cope with that. So the biologists and ecologists will tell you this is why, this is the dominant driver of why these animals are suffering so much. Rates of change. CO2 over the past 2 decades, it's going up about 100 times faster than the last deglaciation, which is when CO2 rose from 180 to 280. The temperature is even more dramatic. It's rising at 170 times faster than that background rate. So again, this is completely out of the ordinary in terms of Earth history. The only time you see evidence of something similar to this is when we have big spikes. There was one 56 million years ago. It has a long name, the Paleocene-Eocene thermal maximum. But again, 66 million years ago when the meteorite struck and knocked out the dinosaurs. Then we saw rapid changes. Those two, by the way, were not as rapid as these. These are the fastest we've seen so far. So if you go to the climate models, and here are the climate models, they are simulating out from where we are here in 2020 to 2100. And you see there are various assumptions about how much more we emit. So this blue line is if we can meet the Paris targets, get our emissions down, stabilize the climate by about 2050. That's the high emission one. Right now we're tracking somewhere in between these two, somewhere toward 3 degrees or so temperature rise. Now when people look at that, they say, well, that doesn't look too frightening. Those curves are fairly gentle, and I see only 2 degrees. Well, if it's a 30-degree summer day and it gets to be 32, well, I can handle that. That's a bit misleading. So what we want to do is put those projections on the same graph. So there's a graph I showed you. We're sitting about here. And if you put those projections, so there's 1900, 2000, 2100's about here, on the same temperature scale. That's what they look like. That's a meteorite strike, or worse. So this is why climate scientists, Earth system scientists, are getting really, really worried that this is an extremely difficult world for us to live in, let alone all the creatures that don't have the technological capability we do. So we're pretty much committed to somewhere around 1.5 to 2. These are the Paris targets, just in here. This is what we're aiming for. Right now, our emissions are going to take us somewhere there. But if we go up 4 to 5, even our powerful civilization, I think, is going to be in trouble. And there are people now, social scientists, who are starting to write about possible collapse and how we're going to deal with that if it comes. But there's a joker in the pack, and this is where I've spent a lot of my own time in the last 5-6 years working on these so-called tipping points, somewhere between 1.5 and 3. And the upshot of these tipping points is if we tip them, the Earth will basically leave our control, and it may simply go up to 4 or 5 without our emissions. So what's a tipping point? Well, if you've been out on a kayak, you know what a tipping point is. You can jiggle that kayak until you jiggle it too much, and you're underwater. So that's a tipping point. So it's a system that you can perturb and jostle around, and it stays around an average value until you push it just far enough, and then it'll flip to something else. Sometimes it takes it a while in the natural world to flip, but it will flip. And the reason it does that is that there are processes within the system that start enhancing your original push. And that's what we've been studying. And we actually have a good handle on what a lot of those look like. Here's a really nice diagram of what tipping points around the Earth look like. So they are ice, they are big biomes like the Amazon, and their circulation. The Enso one, of course, is a big one for us that we have to watch. And they're linked. You see those arrows? So they can act like dominoes. If you set up a bunch of dominoes on the table in a line and you start tipping them, and they tip and tip and tip. There's this tipping cascade that's the big worry, that if we tip enough of these, we could actually tip the Earth system. So we could try to get our emissions down, saying, oh, we don't like this, but it could be too late. This is the real worry now that's coming out. So we did an analysis. There's a group of us, I was involved with that. Tim Lenton was the lead. And we looked at, all right, that last diagram is a wonderful theoretical diagram, but doesn't make any sense in the real world. So we started looking at each one of these. And you can just read in those black squares, each one of those, they're already starting to move. Ice is being lost in Greenland, West Antarctica. Even in East Antarctica, where we thought was stable at 4 or 5 degrees, the Wilkes Basin is starting to lose ice. Atlantic circulation, the north-south circulation, is slowing down. Now this is the big ticket item. You can see how many arrows are linked through there. It affects a lot of stuff. It's slowed by about 15% since a century ago. That doesn't sound like much, but already it is accelerating ice loss here, because this depends on the Atlantic circulation to bring deep cold water up underneath the ice tongues. That's being slowed, so it's trapping more warm water under the ice and it's melting faster. So all these things are linked. We made a little statement in that paper, which I think is important. If these tipping cascades, if these damaging cascades can occur, and a global tipping point cannot be ruled out, then this is an existential threat to civilization. No amount of economic cost-benefit analysis is going to help us. So one of the interesting things we said here is we turned the normal dialogue around climate on its head. We didn't say, can we prove for certain that this tipping cascade can happen? No, we can't prove it for certain. But what we said, if you do a risk approach, you say, can you rule it out? And the answer is no, we can't rule it out. A good colleague of mine who's an expert on the Brazilian rainforest made a really good statement. He says, it doesn't make any sense at all to find out where a tipping point precisely lies by tipping it. And that's the only way you'll find out. All right, so this is a little cartoon that we made in a paper a couple of years ago. It gets used a lot, but it's I think it's a nice way to try to understand what we're talking about. So it's what we call a landscape terrain here, a stability landscape. So basically think of valleys. So time starts there and goes down here, cold to warm, and valleys are stable states of the Earth system. So here we have the glacial, interglacial cycling up here. So every 100,000 years, the Earth does a nice dance this way. The Earth's orbit, when it's down here cold, the Earth's orbit pushes it up here for 10 or 15,000 years, and then it rolls back down. That's normal. But what we've done is we've pushed it out here with our emissions up to 2020. Latest calculations I've seen says we are more than 50-50 chance we've already knocked out the next ice age. Isn't going to happen. And if we go to 2 degrees, we know for certain we're not going to go into the next ice age. But there isn't a terribly well-defined valley. It's sort of rolling around here, very, very chaotic. But we think there's a fork in the road where the Paris targets take us here. Stabilize the Earth. It's going to be hotter than it was there. But we can stabilize it and probably live in it. But if we don't, this tipping cascade can take us over the cliff. That's what the cascade is. And once the ball starts rolling downhill, there'll be a point where we can't stop it rolling. That's the initiation of the tipping point. And then it eventually goes over and it sits here. Hothouse Earth, we think, is very stable. The Earth was in it last about 5 to 6 million years ago. It can stay in it for a few million years. So we're not going to get out of it easily. So this is the name of the game. Where does this fork in the road lie? My best guess is we'll know by 2030. But that could be too late if we do the wrong thing. Right. I'll close now by talking a little bit about the Paris Climate Agreement, where we are and what we need to do, and why this is indeed an emergency. So that's the Paris Agreement, not 2 degrees, but well below 2 degrees. Make every effort to 1.5. How do we do that? Well, we use what's called a carbon budget, and that's because if you look at observations, which are black up to 2010, and if you look at the model projections, they all pretty much fall on a nice line where you can go with the cumulative emission and then back out what the temperature should be. Cumulative means from the beginning of the Industrial Revolution, how much have we added, stacked on year by year. That's what the climate responds to. So there's a nice little number here, 1,000 billion tons of carbon emitted as CO2 gets you to 2 degrees. Nice thing that you can keep that in your mind, 1,000 billion tons of CO2. We've actually emitted about 600, a bit over 600 billion tons already, over half. And that's why we're at about 1.1. All makes sense. Here's what a budget looks like for 1.5. I've actually taken this budget from a more recent IPCC report. We start the counting from 2018. We had 155 billion tons. Actually, this is 2020, so we have to take out the 23 billion tons we've emitted in just 2 years. And that gives us 132. And then these feedbacks I've been talking about, like melting permafrost, we can actually estimate them. That's about 70 for a 1.5 temperature forcing. That takes us to 62 left in our budget, left in our pocketbook. But we're emitting at 11.5 a year. That's 5 or 6 years before 1.5 is gone. Can't get there. Now we can say, let's start reducing now and let's hit 50% reduction by 2020. That only extends it out to about 8 years. So basically, this is why I say 1.5 is gone. We're committed.
The 5 to 6 years starts from which year?
January 1, 2020.
January 1, 2020.
A month or 2 months ago. That's it. Okay. And I haven't accounted, by the way, for the methane and nitrous oxide, which would reduce the budget further. So, yeah.
One of the things which seems to be neglected is obviously that the ocean acid acidification.
Yes.
And one breath in every three of the oxygen was actually down to a healthy ocean.
Mm. Probably more.
And yet, there doesn't seem to be anything going on at all to try and correct the situation.
Yeah, I mean,
Particularly to loss of fisheries,
Yeah.
people
yeah.
will be starving.
If we correct this, we'll go most of the way to correcting the acidification. Most of it's CO2 being dissolved, forming carbonic acid. So you're absolutely right. So there's a lot of this linked up, which is what Earth system science looks at.
You don't think an engineering solution is a
Well,
problem?
you could try to dump a whole lot of alkaline material in there, but I mean, I've done chemistry. I was originally trained as a chemist. I've done chemistry 101, but I don't think that's going to work at the scale it's needed. It's geoengineering the ocean basically,
Yeah.
and you don't know what that's going to do to the marine biota.
No.
It's not going to be good. That's the two degree budget, by the way, which looks a little bit better. So we have 360 billion tons. You do the 2 years we've already emitted. You say, oh, now we better worry about methane and nitrous oxide, so we can make an estimate there. Feedbacks are bigger at 2 than they are at 1.5. But still, here's our budget remaining, 172 billion tons. Now we've got a fighting chance. Current emission rates of 11.5, that would now take us to 15 years, 2035. But if we start emitting, that's just at steady rate. If we start reducing emissions, then you can see that if we get into net zero by 2040 or 2045, we've got a very good chance of the two. So the way I like to put it is, past emissions have already cost us the 1.5. That's dreamland. But if we really get our act together, we can hit 2 or maybe slightly below 2. But it's going to start action now. Where do we sit? That's actually emissions from humans from 1850. Does it show any sign of slowing up? No, it's accelerating, 1.65% a year, exponential growth. Now what I've put on here is scientific work and political agreements. None of them has had any demonstrable effect, 0. So all those work that we scientists put in, all the talks we do, all the massive IPCC reports, nothing. All the meetings in Paris and other places, Kyoto, Copenhagen, nothing. These are driven by economic factors. This one here is the global financial crisis. That's the only thing that's really slowed it down. So, looking there and saying, I'm being an optimist, so I can say by 2040 or 2045, maybe we can hit the 2. What does that curve actually look like? Well, it's been calculated. That's what it looks like. It's the yellow one. There. And so this means that if we can peak emissions this year and then start slowly going down and then really going down, 2040. So when people say net zero by 2050, I say it's a great first step, but you're going to have to ramp it up. It's going to have to be 2040.
Just a quick question. What if the world has a massive pandemic and 50% of the population killed off? Does that make a difference?
Depends on which 50%.
The 4 people that go.
Yeah, that's right.
Would that make a difference?
Possibly. I haven't seen that actually calculated, but that's probably the only thing that'll get you on that orange curve. That's probably a pandemic curve, given present trajectories. So look, the whole point I want to make here is delaying 5 years. That's just 5 years. That's what, 2 electoral cycle and a half. Then it becomes impossible because you have to decarbonize in a decade, and you can't do that. This is applying the carbon budget approach, which is the most robust one. This is why we have an emergency, by the way. So we put this on here. The students are right. They're intuitively right. They haven't done this analysis, but they're absolutely right. They can feel it. That's what they sense. So this was in Stockholm last year on the 15th of March. This was my favorite placard. Let us pause for a moment of science, actually recognizing that science might be important. So just to confirm, scientifically, the students are absolutely right. We are facing a climate emergency. So I've gone through that bit. I'm going to conclude by saying, well, how do we deal with an emergency? That's Christiana Figueres. She was Executive Secretary of the UN Framework Climate Convention on Climate Change. So I was at a meeting with her in Singapore, middle of last year. This was her comment to the Singapore government in a private session. So probably best not to quote that, but anyway, she says, timing is everything, i.e. we have an emergency. The cost of climate change, decades of development wiped out, redevelopment not possible, collapse. She's not a wild-eyed greenie. She's a very sober person. So when someone from the government or someone else says, what's the cost of getting to net zero? It's going to cost us too much. Say, well, the cost of not getting to net zero could well be that. And what's the cost of that? That's what they need to think about. What's required? Transformation the likes of which we've never seen or done before. It's a big challenge for humanity. How does the IPCC treat it? Well, they treat it like this with a lot of negative emissions. This is drawing down CO2. So the only way you can do it with a shallower curve, which might be manageable by 2060, is if you have very big drawdown of CO2. And we don't know how to do that. So we did a little exercise in the Latin paper to say, let's look at a more mathematical view of an emergency. Let's look at two things. Let's look at reaction time. How long does it take you to react? So let's be optimistic. This says 40 to 60 years because it says 2060 to 2080 to zero. Let's just say 30 years, 2050, net zero by 2050. The analogy would be the Titanic approaching the iceberg. At what point can it not avoid it? That's when the reaction time basically hits zero. So then we look at what are the intervention times left for bad things to happen. So that's our net zero. First one, Arctic sea ice. I think we're at about 0 years. We're just on the verge of tipping that. That'll probably be lost. It'll take 2 decades, according to the IPCC. That's probably about right, but we can't get it back. What about West Antarctica? Our best guess is about 10 years. Again, that's shorter than the reaction time. So our intervention time is already gone because we can't react fast enough. So that's probably bound to be tipped. Amazon, maybe 15. Bolsonaro could move that up to 10 if he keeps deforesting at the rate he's going now. But it's drying out from climate change. Again, from that North Atlantic circulation. That is drying out Amazon. Greenland, I don't know, but maybe 25 years. That's a huge ice sheet. It is melting, and as you can see, a little hard to see, it's accelerating. But all 4 of those are shorter than our reaction time. The question is that enough to start the cascade? So the question we asked in this paper is, are we already losing control of the system? We don't know, but it's a pretty frightening thought. So there's Canberra again, going back to the fires, Tuggeranong. So what about our climate policies? Are we going to meet that 30-year reaction time? Well, you know the answer to that. We ranked 57 out of 57 countries assessed. This is by a German policy NGO, which ranked policies of countries around the world. We were last. In action, we weren't quite last, and that's because states and local jurisdictions are doing something. As you know, we're promoting more coal and gas and unconventional gas, even as the fires were burning, even as the reports come out. So Australia's policies, if everyone did this, would lead to a 3 to 4 degree world without the feedbacks factored in. So basically, our government is heading for hothouse Earth, if everybody did that. And I would say that the odds are very high probability you'd hit hothouse Earth. Well, the last thing, I don't want to leave you feeling really dreadful. I don't want to leave myself feeling really dreadful. No, it's not too late. So how do you deal with an emergency when everything's going pear-shaped? Well, here's what I think you do. The only thing you're going to do is create a social tipping point. Tipping points can happen fast. They've happened before in human societies. So let's look at Australia and the case of coal. That's the south coast, by the way. People having to be evacuated by the Navy because they couldn't get out there. So what's happening with coal in Australia? Extreme weather. For the first time, I've heard a lot of people linking coal to the fires, to extreme weather. They're starting to make that connection. That is a huge step. Technology and economics. We all know now that if you want to roll out new power stations, it makes no sense whatsoever to put in a fossil fuel plant, and that's economically. Renewables are now cheaper, much cheaper. And that's getting a lot of people's attention. Legal, Rocky Hill case. A coal mine was stopped in Gloucester, up from Hunter Valley, New South Wales. And part of the reason was climate change. That was an interesting experience. I was the expert witness in that one against the coal mine. And it was a good exercise for me to be forced to think like legal people. I don't think I've ever quite recovered from that yet, but anyway. Investor pressure. So some coal companies are starting to feel the heat. Glencore say it's going to cap coal production. And social pressures, the student strikes, demonstrations. Some of you were at Parliament House a few weeks ago, and so on. None of these on their own are going to tip our government, or tip the system. But as they build up pressure, things can happen very fast, particularly in the investor world. They're not there to lose money, and when they sense that there's going to be a stampede, the last thing they want to do is be on the wrong side of the stampede, because then they're left holding the debt. So there's going to be a point where something's going to spook the market, and coal is going to go. And an expert on this told me last week he thinks within the next 5 years, coal is going to be tipped out of the system.
Our current development policy is to have a hydrogen economy that wants to burn coal and natural gas to
Yep.
produce hydrogen.
Yep.
That's from Dr. Alan Finkel.
Yeah, I know that. I know Alan. Yeah, and well, if they tip coal out, it doesn't matter if they're going to make hydrogen or electricity directly. It's going to get tipped out. But that's a global thing they're thinking about. But we'll get sucked into that. Social tipping point globally, that's Greta, famous Swedish girl in front of the Swedish Parliament. Student strikes and civil disobedience. Globally, they're getting very big. Divestment from fossil fuels, and that is moving internationally quite strong. And Australia is not immune from that no matter what our government wants to do. The big end of town, if it smells it's going to get left holding a big debt, is going to move no matter what Morrison and Taylor want to do. Rapid technological development, not only in electricity, but in transport and other sectors. So things are really moving there. Not fast enough, but they're moving. Increasing political instability. USA is becoming more and more unstable. Trump will almost surely get back in, but California is going to go its own way, and so will some other states. It's becoming more unstable. Here in Australia, we're becoming more unstable too. Trusted voices are demanding action. The fireys, for example, and the Farmers for Climate Action. People at the community trust is not being wild-eyed greenies or loony scientists. People that actually are out there making a living on the land, fighting fires, and so on. They're now saying, this is getting out of hand. So again, all of these things add up. And the corporate sector is starting to get spooked. I was just down in Melbourne last weekend doing a course in 2 days with a lot of corporate people. And I've done it for 6 years in a row. This is the first year where they said, all right, we've got to learn about climate change, and they go back and do this thing. Now they're just begging for information, and you can see the wheels turning over. Are we going to be left with bad stock? That's what they're worried about. So I'll conclude with this. This is Parliament House, Canberra. Don't you love the humor that Aussie students have? They make that nice Swedish connection there. But actually the one I like is this one, system change. That this isn't just a little change we need, it's a fundamental system change that needs to happen. So I've taken a lot of your time, and I'm going to stop there and pause for a little bit of thought and a lot of questions. I'm sure there's a lot of questions out there.